Okay, so our objective was to construct the Cayley table for the symmetric group S3, where we had the following to start. Sigma is the cycle 1, 2, 3, and tau is the cycle 1, 2. And we established the following relations last time, that because tau is just a swap, we're going to convert to this notation. Tau squared is the identity, because if I swap and then swap again to come back to doing nothing, and we also found that tau cubed, sigma cubed, was the identity because this is essentially a rotate. I send 1 to 2, I do it again, I send 2 to 3, I do it a third time, I send back to 1, so that became the identity. And the thing that was left to show was a way to rewrite sigma tau. So I want to start there. That's by the cycle definition. Composed with 1, 2. So what does that mean as a straight cycle? Well, I always start, when I compose functions, I start on the right. So it's 1 gets sent to 2. But then the second function sends 2 to 3, so 1 gets sent to 3. So now I should immediately figure out where 3 goes. Well, this doesn't touch 3. This sends 3 to 1, so we're back, and that's it. What about 2? Well, 2 gets sent to 1 by the first permutation, but then 1 gets sent back to 2, so 2 gets sent to 2. So that's the end of sigma tau. And then we were to show that that's the same as tau sigma squared. So that's a lot of stuff. That's 1, 2. 1, 2, 3. 1, 2, 3. So let's see if we can trace all the elements. 1 gets sent to 2. And then 2 gets sent to 3. And then 3 doesn't get sent anywhere, so 1 gets sent to 3 by the overall composition, right? Then we look at 2. Then we look at 3, because it's over here. So 3 gets sent to 1. But then 1 gets sent to 2. But then 2 gets sent to 1, so 3 gets sent to 1, and we close our cycle. And all we have to do is figure out what happens to 2. 2 goes to 3 in the first permutation that acts. And then 3 goes to 1. And then 1 goes to 2, so 2 ends up going to 2, right, all the way through. So that's it. So those really are equal to each other, as we wish to show. And now we've established our 3 relations. So I'm going to put that relation over here. Sigma tau is the same as tau sigma squared. And now let's put up the table and see if we all agree on the Cayley table for this thing. See how red likes to write today. So we're going to start with composition, and then E, and then sigma, and then we show that sigma squared is an element, and then tau, and then tau sigma, and finally tau sigma squared. And then running down, I have the same elements. Identity, sigma, sigma squared, tau, tau sigma, and tau sigma squared. 6 elements. So what do we know? We know the identity just leaves everything alone, right? So I can fill those in real quickly. We have those on the board. E sigma sigma squared, tau, sigma, tau, sigma squared, and also down sigma, sigma squared, tau, sigma, and tau, sigma squared. And then sigma is just sigma squared, and sigma squared times sigma is sigma cubed, but now we use our relation that sigma cubed is the identity, and then the same thing here, sigma times sigma squared is sigma cubed, which is the identity. Background noise drop a little bit. Okay. What else is easy? Well, tau sigma is an element, so we have tau sigma here. Tau times sigma, and tau sigma times sigma is tau sigma squared. That's one of the elements. And now we have to start doing some work, right, to fill in the rest. Well, we have that sigma times tau is tau sigma squared. Right? The identity we just showed. Let's finish this row. We're going to do sigma tau sigma. Well, what does that mean? That's this and that. What do I do to resolve that? Using just the identities. Well, the only thing recognizable here is tau is sigma tau, right? But that's the same as tau sigma squared sigma. And that's the same as tau sigma cubed, but what is sigma cubed? Identity. This is tau e, which is tau. So that's how you use the relations. This is what I want to focus on. So this is just tau. And now how about sigma times tau sigma squared? The next one. Well, I already know. Well, let's just do it again. So I can group them this way. And sigma tau is tau sigma squared times sigma squared, which is tau times sigma cubed, right? But sigma cubed is the identity. So tau sigma is the answer. So this is easier. Once you have these relations, I can use them to convert any answer without actually doing all the work with the cycles. So let's try to work through this next row and see what we get. Sigma squared times sigma squared is easy. What would that be? That's sigma to the fourth, which is just sigma. Right? Now, let's work some more of this using just my relations. The next one I want is sigma squared times tau. Well, that's sigma times sigma tau. Well, what's sigma tau? Tau sigma squared. Does that help us at all? Well, kind of. We can now call that sigma tau times sigma squared. Well, what's sigma tau? We use it again, right? It's tau sigma squared times sigma squared. And sigma squared times sigma squared is actually sigma, right? Because the cube cancels out. Okay, let's do the next one. Sigma squared times tau sigma squared. Is that where I am? Times tau sigma. Yeah, that's it. What am I going to do here? Well, I already know what sigma squared tau is, right? This is the same as tau sigma, as shown above, times sigma, and that's tau sigma squared, and that's an element. So I can use my previous work to help me with this. And then finally, sigma squared times tau sigma squared. Well, again, I can use my previous work, right? I know that sigma squared tau is just tau sigma. And that's tau times sigma cubed, which is tau. So that's the idea. Let me just fill out the rest of the table, because I've done my homework. This is sigma squared. And then tau times tau is the identity. That's easy. I'm using E, so I better stick with my convention. And then tau times tau sigma, that's easy. That's tau squared sigma is sigma. And again, tau times tau is tau squared times sigma squared is sigma squared, so that one's easy. And then tau sigma times sigma squared is tau sigma cubed. Sigma, and the last row goes something like this. So is that what you end up with? No? But using this relation notation makes this a lot easier than doing cycles, and it ends up being easier to work with when simplifying. This is a big theme. It's called element pushing, but I simply do the algebra and then use my substitution rules to get something I need. This thing only has 6 elements. So this is the Cayley table for S3. And a little example of working with what this is called is generators and relations. The generators are sigma and tau, and these relations define how the algebra goes between them. And it's used a lot to establish the structure of groups. Okay, the next thing I want to look at is the subgroups of this, of S3, and they should be easy. How do I make subgroups? What's the easiest subgroup always? Just the identity. So I know that the identity by itself is a subgroup because it's closed, has identity, and inverses, right? So to get something more interesting, I always have to have E in a subgroup, right? Let's try throwing an element in. So I throw in tau. If I just take those 2 elements, do I have closure? Well, what's E times tau?
Tau.
Tau. And tau times E.
Tau.
And there's only one other question. What's tau squared? E. So this is closed. It has identity. Does it have inverses? Well, the identity is always its own inverse. What's tau's inverse? Tau times what is the identity? Tau. So it's its own inverse. So this is a subgroup. It passes the 3 tests, right? Identity, closure, and inverses. So this is a subgroup. Another one. All right, what else can we do? How about if I start off with E and I add sigma? Well, E times E is E. Sigma E and E sigma are sigma. The only thing left to worry about is sigma squared. What is sigma times sigma? And that's one of the elements, so I have to write it down. So if I start here, I have to add sigma squared. Now, am I done? Sigma times sigma squared is the identity, and sigma times sigma is sigma squared. How about sigma squared times sigma squared? It's just sigma. This is closed. What's the inverse of sigma? Sigma squared, right? Because I multiply sigma squared times sigma, I get the identity. And what's the, well, by definition then, sigma squared inverse must be sigma. So everybody's got an inverse. This is a subgroup. So we have 3 subgroups so far. Can we make any more? Well, in this one, I started off just with tau and the identity. Here I started off with just sigma. So let's try to do just E, tau, and sigma and see what we get. Well, I know I'm going to get sigma squared, right? It has to be in there because sigma times sigma has to be closed. So I need sigma squared. What else am I going to get? What other new element am I going to get? Tau sigma, right? This tau times sigma has to be in there.
Tau sigma squared.
Yeah, now because I've got sigma squared, I've got tau sigma squared. And how many elements is that? That's 6. That's the whole thing. So any attempt to add another thing gives me the entire. So I only have 2 proper subgroups of S3. So one more thing I want to show. We're going to construct the table, and we're going to look at the subgroup structure. This is a helpful diagram kind of thing. I actually create a graph where I put the group at the top and then listed subgroups. So over here, I have a subgroup. It's E tau. And over here, I have a subgroup that's disconnected. It's E sigma and sigma squared. And then these are both supergroups, and E is a subgroup of both of these. So that's my subgroup tree for S3. Okay, why is this interesting? Why do we care about permutation groups like this? Well, I want to now reveal what's behind the curtain. Awe is like. How can I move this figure, this triangle, to make it look the same with only a change of where the labels are? That is, what can I do to this triangle geometrically to end up looking exactly like this, just with the labels different? I can rotate it, right? I can send A to B, B to C, and C to A, right? Well, that's what this guy does. He rotates the triangle by 1/3. And 3 rotations bring me back where I started. What else can I do? Well, I could draw a line of symmetry here, and I could flip about that line of symmetry, swapping A and B. Well, that's exactly what tau does. Sigma and tau represent the symmetries of a triangle. And if I do them all, I get the full group. And as I compose the rotation with the flip, etc., I get them all. So this is one reason why these are important. And that's a good place to stop for our first segment.